Can I calculate area steel without using a table? Yes, you can. Really? Yeah, you can, but you cannot realize that you can. Anyway, if you have a cross section and the area steel is unknown, we have B, we have D. So right now I'm talking about M ultimate is known. I can figure out the value of M ultimate. Cross section is known. I can figure out the cross section. But the issue is I cannot figure out the area steel, and I don't like to use a table. Can I get the area steel? Yes, you can. Very simple. Very simple. Between reinforcement and concrete on the top side of the cross section, we have something called neutral axis. We have strain distribution. We learned all of this stuff before. Epsilon steel and epsilon concrete, which is 0.003. We have stress distribution. We have compression stress block with depth A, and the total depth for the neutral axis is C. This value of stress 0.85 F prime C. And we have here a tension force in the steel reinforcement, which is unknown. And we have compressive force here, capital C. Everybody agree with this layout? Anybody has any question for this point? I think we are good. We learned from equilibrium, capital C equal capital T. So 0.85 F prime C A B, that's right, equal area steel time F yield. Unfortunately, in this equation, we have two unknowns. Area steel is unknown. A, the depth of this stress block is unknown. This is the first equation. Everything is known. Everything else is known. We have two unknowns. Anybody has any question until this moment? We learned. We have something called MN. Nominal moment. Do you remember? Equal area steel F yield time D minus A divide 2. If you multiply this nominal moment by phi, so the other side will be multiplied by phi. That's right. That's right. Your design, we are looking for area steel that make M ultimate from structural analysis smaller than or equal phi Mn. So I'm gonna assume M ultimate equal phi Mn. So this equation can be M ultimate instead of phi Mn equal phi area steel F yield D minus A divide 2. If you are looking for this equation, which is equation number 2, M ultimate is known. Phi, I can assume 8.9. Area steel is unknown. A is unknown. So if you go back to the first equation with unknowns A and area steel, and the second equation with unknown in area steel and A, I can solve these equations together to figure out what is the value of area steel, what is the value of A. I don't care about the value of A, I can get the value of area steel required without using any table. But we did more calculations. We set up two equations, equation number 1, equation number 2, and solve these equations together to figure out the required area steel. Instead of that, we are using table by a value M ultimate divide phi B D square. This value can figure out the value of rho and directly the value of area steel without any more calculations. Did you get it? Because last meeting, Burak, he isn't here today, asked me what will happen if we have something different than in the table. F prime C, it's not 3,000, it's 3,500. So it's not included in the tables. How can I figure out the area steel? You can figure out the area steel from first principle. Do you remember I told you this layout is very important. From this layout, we can design, we can do anything in this course. Basics. Okay? And this one, capital C and the capital T, basics. And the concept, nominal moment equal T time this level R. So we can figure out anything with these basics. Any questions so far? Any questions so far? Okay. We have a new topic today, which called TSection. TSection. Guys, what we covered before, I covered a rectangular beam. What you mean? We have a rectangular like this beam. This beam, reinforced concrete beam, the cross section for this beam is rectangle. Looks like this one with B as the width and overall depth and actual depth D with area steel. We learned how to calculate everything for this cross section. If everything is given, area steel is given, I can figure out the design moment. If M ultimate is given, I can figure out the required area steel. So we have two situations. We covered all of this stuff. But sometimes, it's not sometimes, most of the times, your cross section or your beam is connected to slab, concrete deck. So this beam with this slab will make different shape of cross section, which you call T-section. And that makes sense. We have a slab in your building. You are walking on floor. This floor, I'm not talking about wood building. I'm talking about concrete, reinforced concrete building. This is slab made from concrete and beam made from concrete. This beam with this slab are poured or placed monolithically. So they are making one unit. This unit called T-section. Okay? T-section. Part of the slab is working with this beam to make T-section. By the way, this part of the beam can be called web. This part of a slab which is working with this web called flange. This flange and this web can make the T-section. According to ACI, if you have a web connected to slab part, only part, not all the slab is working with the beam to make T-section. No, we have only a part. This part has width called B flange, or sometimes B effective. So if you have a beam with it connected to a slab, how can I figure out the effective width of this slab which is working with this beam to make T-section? We have three conditions. I'm gonna use the least value. According to ACI, American Concrete Institute 318, ACI 318 for 2018. Span of this beam divide 4, we have a value. 16 H flange plus B web, we have another value. Or center line to center line. As you see here, we have a beam here. We have another beam. We have another beam. We have a distance between this one and this one, center line to center line. So this is a value. We have another one, 16 H flange. This slab has thickness equal HF flange. Plus B web, the width of this web. Or span divide 4. So we have three values. Which one I'm gonna use? The least value. The least value. For example, the third problem in your homework, calculate the effective flange width. We are looking only what is the value of B effective. For the shown cross section, if the span length of the beam equal 24 feet. So we have three values. Let's start with the first one. What was the first one? Span divide 4. What is the span of this beam? 24 feet. Divide 4. Please multiply this feet by 12 to be an inch. So this value will be 24 times 12 divide 4 equal 72 inch. Second condition or second value, 16 H flange plus B web. 16. What is the thickness of this slab or this flange? What is the thickness? How much? 4. Plus B web. What is the value of this web? What is the width? B web. How much is given? 12. We have a value 16 times 4 plus 12. 76 inch. Third condition. Center line to center line distance. What is the distance between this center line and this center line? What is the distance? How much? 4 feet 0 inch. So 4 feet times 12. How much? 48. So final decision. Be effective for this T section. This web with part of the slab will make T section. This width of the slab that make T-section will be 48 inch. Least value 48, 76, 72, least value will be the effective flange width. The effective part from the slab will work together with the beam to make T-section. Any question for this point? Guys, any question for this point? Very easy. Very easy. Quarter span, web width plus 16 times slab thickness, or center line distance between webs. Sometimes I'm talking about T-section. I'm talking about intermediate beam. Sometimes your beam will be at the edge. Of this slab. If you are talking about intermediate beam, so we have a beam connected to effective width of the slab. This shape will be T-section. But sometimes we have edge beam. So what is the part of the slab is working with this beam, this part. So the formed shape will be L section. This one L, not T. L section or L beam. We have a flange on one side of the web only. So the effective width, B effective, equal 1/12 of the span, span divide 12, or web width plus 6 times 6 H flange plus B web, or half distance center line to center line. So we have three values. We are going to use the least value. So if your beam on the edge of the slab, we have L shape. So we have a different limits for B effective. Span divide 12, 6 H flange, this flange, thickness, plus B web, this B web, or half distance, this distance between this center line and this center line, we will use the half distance. And I'm gonna use the least value. So please be careful. If you are talking about intermediate beam, so we have T-section. We have a limit for B effective, 1, 2, 3, and we will use the least value. If you are talking about edge beam, so we are talking about L section. So we have a different values for B effective, and we are going to use the least value. Any questions, so guys? Any questions so far? Guys, any questions so far? So yeah, this one is T. So okay. Let's start. How to design of T-section. Design of T-section. Very simple, very easy. You learned the basics. So right now we have B effective at the top of the cross section, and we have B web, and we have area steel. and we have H flange, the thickness of this flange. I'm gonna assume the neutral axis within the flange. I'm gonna assume the neutral axis falls in the flange. Like first principle, anything above neutral axis will be under compression. Anything below will be under tension. Concrete in tension will crack. So we have only steel reinforcement. So we have tension force here, T. We have compression force here, capital C. The value of capital C equal 0.85 F prime C A B effective. Do you remember last week? Capital C equal 0.85 F prime C A B, which is this one. Which is this one. No, this time we are talking about this area of flange under compression. So what is the width of this area? Is B effective. B effective. Not this width as normal. How can I figure out the value of B effective? Go back. Are you in this case or this case? 90% will be in this case. Anyway, what is the value of capital T? Area steel time F field. The only unknown in this equation is A, the depth of the stress block. If you can figure out A, please make sure that this value of A is smaller than the flange width to make sure that the neutral axis is still within the flange. Then your nominal moment equal area steel F yield times D minus A divided 2. Then if you would like to get the design moment, this design moment equal phi area steel F yield times D minus A divided 2. And the phi most of the time will be 0.9. But you can figure it out by the value of epsilon steel. You remember a table? We have a table. We can use the value of strain in steel to figure out the value of phi. Guys, remember, effective flange width B effective is used instead of B web, this width. We will not use it in T section. If your beam is a T section. Let's do an example. Very simple example. This one. Determine the design strengths. We are looking for what is the value of phi Mn of the T beam in the shown figure. Use a concrete F prime C, steel reinforcement grade 60. The beam, here you go. The beam has a span equal 30 feet and cast integrally with 4-inch thick floor slab. This slab has a thickness 4 inch. And the clear distance between whips is 50 inch. Wow. Wow. So I'm gonna ask you guys, everybody can tell me what is the value of B effective? Go ahead and calculate it, please. We have 3 values. What will be the first one? What will be the second one? What will be the third one? Be careful about this one. Be careful about this one. I'm gonna do it here. So we have span divided 4, 30 divided 12 divided 4. We have 16 H flange plus B web. So we have 16 times 4 plus 10. We have center line to center line. Center line to center line. Be careful. Center line to center line. 16 times 4 plus 10. 4. Center line to center lines. Any answer? Let's see. Guys, any answer? We have span divide 4. We have 16 H flange plus B web. We have center line to center line. So any answer? What is the value of B effective? This width of flange. Okay. Guys. No answer? You are spending too much time for nothing. Time is a key. Okay, so it looks like no answer. Okay. Let's do it. Span divide 4. Span 30 feet. Span length of this beam equal 30 feet times 12 to be an inch, divide 4. So what is the value? Second one, 16 flange thickness plus B web. 16 times this flange thickness 4 plus this web 10. What is the value? Then center line to center line. We have here an information, the clear distance between web. What does it mean? This one in the real life looks like this. We have many beams arranged together parallel to each other. The problem, the information said clear distance. Clear distance means distance between this side to this side. How much? 50. But we are looking for distance between center line and center line. So anybody can tell me what is the distance between center line and center line? So you have to add here from this side 5 and from this side another 5. So it will be 60 inch. So center line will be 60. 16 times 4 plus 10 will be 74. 30 times 12 divide 4 will be 90. So we have 3 values of B effective. I'm gonna use the least value. So the value of B effective in this problem equals 60 inch. Equal 60 inch. Yeah, thank you, Alan. Alan, 50 is wrong. 90, okay. 74, okay. But 50, be careful. Clear distance. No, I didn't say clear distance. I said center line distance between webs. So if the clear distance is given, you can figure out the center line to center line. Okay. Next step is nothing. We have capital C equal 0.85 F prime C A B effective. Be careful. So we have also capital T area steel time F yield. What is the value of area steel? It's given 6 inch square. So 0.85 time F prime C, how much? 4,000 time A, I don't know. What is the value of B effective? 60 equal area steel 6 inch time F yield 60,000. The only unknown in this equation is the value of A. So 0.85 times 60 divide 6 times. It will be 0.567 inch. One more time. 0.85 times 4,000 times 60. Oh, no, I have something different. Sorry. No. It's wrong. This value is wrong. This value equal 1.76 inch. I'm sorry. I have to make check. Check what? I assumed the neutral axis falls inside this flange. And this depth of the stress block A must be smaller than the thickness of the flange. So make sure this A is smaller than H flange, which is 4 inch in our case. Yes. Okay. Keep going. Nominal moment equal. Before nominal moment, anybody can tell me what is the value of C? Do you remember we have a value of C, which is the actual depth of neutral axis equal beta 1 times A. Do you remember how can we figure out the value of beta 1? Yeah, we have a table. F prime C equal 4,000. So beta 1 will be 0.85. So we have C equal 0.85. I'm sorry, guys. I'm so sorry. A equal beta 1 times C. I'm so sorry. So C will be A divide 0.85 will be 2.1 inch. Anyway, what is the value of nominal moment? Equal area steel F yield times D minus A divide 2. Area steel 6 inches square. F yield 60,000. Depth. What is the value of depth? Is given 24. Depth for the center line of the steel reinforcement 24. Minus A 1.76 divide 2. So your final value of MN will be 6 times 60,000 times 24 minus 1.76 divide 2. This one will be 8323.2 kip inch. If you divide it by 12, it will be 693.6 kip foot. But we are looking for design moment. Design moment will be phi mn. Do you remember how can we figure out the value of phi? Value of phi. We have strain distribution, epsilon steel, epsilon concrete equal 0.003. This neutral axis at depth equals C, small c, 2.1. So the remaining distance will be D minus C equal 24 minus 2.1 will be 21.9. Can you do triangle similarity between this triangle and this triangle? Yes, I can. 0.003 divide epsilon tension equal this value 2.1 divide this value 21.9. So I can figure out the value of epsilon t. It will be 0.031. Yes. So this value greater than 0.005, so phi will be 0.9. Your design moment, phi mn, will be 0.9 times mn 693 point something, 0.6. Your final answer will be 0.9 times 693.6 will be 624.2 kb foot. Guys, I told you before, we are talking about long story. In a different meeting, probably last week, as I remember, we learned how to get the design moment by multiplying it by phi. And we learned how to figure out the value of phi based on the strain in the steel reinforcement. How can we calculate the strain in steel reinforcement using strain distribution by triangle similarities? Based on the value of epsilon tension in steel, I can figure out the value of phi, then I can figure out the value of design moment. So the only thing we added today, we need to calculate the B effective, the effective width of flange, which is working with this web. So we have a web, we have a flange. This flange has effective width. It's not given. We need to figure it out. Once you get it, go ahead and do your calculation as normal. But be careful. Capital C, which is a compressive force in concrete, I'm going to use the B effective rather than the normal or typical B, which is the web width. And keep going to finally figure out the value of the design moment. No, we will not use a table because this table or these tables only for rectangular section. I'm sorry, Omeri, you have to use the first principle. Even if area steel is not given. Okay? These tables only for rectangular section. If you are talking with something different, we are using the first principle. Also, area steel here is given. So we are looking for M design moment. So we have to use the first principle. Okay. Any question? I'm gonna stop here. We still have one more part. This one. And one more example.